Hello friends, welcome to my YouTube channel. My name is Prathmesh. Without wasting our time, let's begin. And if you like, please like, share and subscribe.
Modern cyber threats move at machine speed, ripping through static defenses before human teams can even triage the alerts. In a standard software development lifecycle, code moves from planning to testing and deployment. But notice this bottleneck near the end, the security audit. When defense is applied here, flaws pile up, creating critical delays before going live. To address this specific architectural weakness, OpenAI launched Daybreak on May 11, 2026, built on the GPT-5.5 architecture. The platform is designed to detect, validate, and patch software vulnerabilities at the same speed attackers exploit them. Securing modern infrastructure requires moving defense away from a final audit and embedding security checks directly into every phase of development. Daybreak operates as an embedded engine, working alongside developers from the initial line of code to replace the traditional disconnected audit. Legacy static application security testing simply scans code and generates text alerts. Modern development requires active remediation. Compare these capabilities. On the left, a passive scanner merely outputs warnings. On the right, Daybreak's Codex security framework generates code, tests it in a simulated loop, and produces a validated patch, iteratively reasoning, acting, observing, and refining. These agents operate directly within existing code repositories, rather than pulling code into an isolated security sandbox. Against automated zero-day exploitation, closing the window between discovery and repair is the only reliable defense. Machine speed remediation provides that capability. Integrating the Codex security framework turns a rigid static assembly line into a self-healing architecture. We can see this in practice by mapping Daybreak across the pipeline. During the planning and design phase, a threat modeler module docks directly into the workflow. Standard threat modeling relies on manual documentation that is often obsolete by the time actual coding begins. Daybreak automatically ingests system requirements and architectural plans at project inception. It generates dynamic, editable threat models, mapping out potential attack vectors before developers write a single line of code. Rather than burying architects in a list of theoretical risks, the system prioritizes reproducible, high-impact vulnerabilities. As the project scope shifts during development, these editable models update continuously. Injecting AI at the planning stage neutralizes structural vulnerabilities before they are ever written into the codebase. Moving to the development and integration phase, a continuous detection module locks into the pipeline. As developers commit code, Daybreak acts as a parallel agent, observing the repository in real time. It applies reasoning to massive, unfamiliar code bases, looking for deep architectural flaws that standard syntax checks miss. Two individual components might appear secure in isolation. Daybreak maps the interactions between them to trace realistic attack paths that only emerge as systems integrate. It also performs dependency risk analysis, ensuring third-party libraries do not introduce hidden backdoors. This provides real-time architectural awareness, evaluating code as part of a complex, living ecosystem. The pipeline then advances to the build and test phase. Here, the automated patching module docks, putting the Codex security framework into action. Identifying a vulnerability is only half the battle. The pipeline must autonomously close it. Daybreak first generates a specific code fix tailored to the logic of the repository. The AI then writes and executes its own unit tests. It validates the patch in a sandbox to ensure it resolves the flaw without breaking existing dependencies. Once validated, the patch is committed directly back into the repository for human review. Security teams can focus on approving pre-validated, machine-generated fixes, rather than writing custom patches from scratch. This automated loop matches the speed of defense to the speed of modern agile deployment. This brings us to the final audit phase, completing the fully integrated pipeline. Deep system analysis presents a problem. The same tools required to dissect malware or identify architectural flaws can also be used for offensive exploitation. Standard GPT-5.5 models use strict safeguards to block these advanced, potentially dangerous maneuvers. OpenAI addresses this through a tiered access model that segments capabilities based on identity verification. The middle tier, Trusted Access for Cyber, or TAC, is restricted to verified defensive security teams. TAC reduces standard refusal boundaries, allowing defenders to perform complex malware analysis and patch validation without triggering standard safety filters. This provides necessary operational freedom for defenders, while walling off offensive tools from standard enterprise instances. The highest and most restricted tier is GPT-5.5 Cyber. This tier is strictly authorized for red teaming and requires highly vetted, specialized workflows. It enables binary reverse engineering, allowing the AI to decompile software and find flaws hidden within compiled code. Red teams use this model to simulate advanced persistent threats, testing their own automated defenses against machine-speed logic. GPT-5.5 Cyber acts as the ultimate stress test, ensuring that integrated pipelines can withstand high-level automated attacks. From threat models at project inception to automated patching, the Daybreak pipeline creates a continuous loop of defensive data. The platform is supported by an early ecosystem of major cybersecurity partners who integrate their threat intelligence directly into the system. This includes partners like Cloudflare, Cisco, CrowdStrike, Palo Alto Networks, and Fortinet, who feed external data into the central core. Organizations are currently onboarding in phases through OpenAI's Request a Vulnerability Scan portal. The launch of Daybreak is OpenAI's direct answer to Anthropic's Mythos system, developed under Project Glasswing. The deployment of these competing systems by OpenAI and Anthropic establishes agentic remediation as the new commercial standard for enterprise defense. Organizations that fail to embed machine speed remediation into their development lifecycle will be architecturally incapable of defending against the next generation of automated threats. On May 11, 2026, OpenAI launched Daybreak, a security platform designed to detect, validate, and patch software vulnerabilities at machine speed using the GPT-5.5 architecture. Legacy security operations rely on passive code-based querying, scanning for known errors, and generating heuristic alerts that require manual investigation. Daybreak introduces an active, agentic framework that executes responses autonomously. This diagram illustrates the objective: achieving a true shift left in defense. By embedding the agent directly into the development lifecycle, vulnerabilities are validated and patched the moment they appear in the code. This architecture acts as OpenAI's direct counteroffensive to Anthropic's highly restricted Mythos system. To evaluate how Daybreak functions, we need to deconstruct its 4 operational pillars. We also have to examine the cryptographic tiered access matrix OpenAI built to govern its use. Understanding this platform requires looking at how an artificial intelligence transitions from generating text to securely modifying enterprise code. Traditional static application security testing, or SAST, suffers from a critical limitation. Rules-based scanning generates an unmanageable volume of false positives. This logic tree illustrates how Daybreak addresses the noise problem through its first operational pillar, vulnerability detection powered by GPT-5.5. Instead of checking known signatures, the model reasons across massive, unfamiliar codebases to identify subtle logic flaws. It then uses these structural weaknesses to construct and validate realistic attack paths, confirming that a theoretical exploit is actually viable. The framework then moves to its second pillar, automated patching, driven by the Codex security framework. This shifts the output from a simple notification to an actionable fix, generating the precise code required to remediate the vulnerability. Codex then tests these generated patches directly within the organization's existing repositories to ensure the fix maintains system stability. The topological map generated here represents the third operational pillar, threat modeling. Based on observed architecture, Daybreak automatically maps out editable threat models, filtering out theoretical risks to strictly prioritize reproducible, high-impact issues an attacker could execute today. Finally, the system scales up to its fourth pillar, system analysis, built specifically for complex, high-tier threat environments. At its baseline, this component audits dependency risks and deconstructs incoming malware, but its most advanced function is performing complete binary reverse engineering on compiled executables. Collapsing the gap between vulnerability detection and patch deployment systematically forces the mean time to respond, or MTTR, down to near zero in modern DevSecOps environments. Automating these 4 pillars gives defenders a significant structural advantage. However, releasing an AI capable of autonomous binary reverse engineering carries severe dual-use vulnerabilities if weaponized by bad actors. This creates a strict deployment problem. OpenAI must distribute an AI capable of writing functional exploits without handing the public a scalable cyberweapon. This matrix table outlines the solution: OpenAI's dynamic access model based on strict identity verification. The baseline tier, GPT-5.5, is provisioned for general developer and enterprise use. At this level, the model maintains standard safeguards and intact refusal boundaries, suitable for everyday knowledge work. The critical shift happens in the middle tier, Trusted Access for Cyber, or TAC. Authorizing access requires organizations to provide cryptographic proof that they are verified defensive security teams. Once verified, the standard refusal boundaries are deliberately reduced. The model is permitted to ingest active malware and validate functional exploit patches. The highest tier is GPT-5.5-Cyber. Reaching this level requires passing extreme vetting processes and operating within highly specialized workflows. In this tier, organizations are authorized to conduct active red teaming, penetration testing, and unrestricted binary reverse engineering. By cryptographically linking model behavior to a verified organizational identity, OpenAI established a viable architecture for deploying agentic cyber capabilities at scale. Moving from theoretical access models to practical deployment requires executing a specific set of procedural steps. This flowchart maps Daybreak's phased rollout process, originating at the Request a Vulnerability scan portal. Organizations begin by submitting initial operational data at this entry node. The data then enters the identity verification pipeline, where the account is evaluated for elevation into the TAC or GPT-5.5 cyber tiers. Once cleared, the organization can integrate Daybreak's automated checks directly into their existing CI/CD pipelines. This network map shows deployment is supported by security partners, including Cloudflare, Cisco, CrowdStrike, Palo Alto Networks, and Fortinet. It relies on these partners to gather threat intelligence, establishing a unified, cross-platform defensive posture. Installing software is no longer the bottleneck. Successfully activating the necessary defensive ecosystem is almost entirely an exercise in proving organizational identity. Daybreak proves that true shift-left security is possible. By combining machine-speed reasoning with automated repository patching, vulnerabilities can be resolved as quickly as they are coded. This new Daybreak architecture now stands as the primary market counter-architecture to Anthropic's highly restricted Project Glasswing system. The cybersecurity arms race has evolved past the goal of simply deploying the most capable language model. The tactical advantage now belongs to whichever platform can safely distribute offensive-grade automation to defensive teams without compromising global security. Moving forward, enterprise network survival will depend on rigorous, identity-based frameworks like TAC to wield autonomous defense against automated